Alright, so let's start chapter 9. Chapter 9 talks about competition between SN1 SN2 E1 and E2 reactions, which we've already been kind of talking about some, and the sheet that I sent out or handed out right before spring break slash sent out in an email a few days ago describes how we would decide which of these mechanisms is taking place. But let's dive in a little bit deeper as to why these things occur. And so the first question on that sheet that I gave you or sent out an email the other day is the carbon containing the leaving group primary, secondary, or tertiary? So you want to identify your carbon that has the leaving group and then identify how many carbon groups are attached to it to determine whether it's primary, secondary, or tertiary. Primary carbons will be an SN2 mechanism unless a bulky base is used, then it would be E2. An example of a bulky base would be tert butoxide. And remember, there's got to be some type of counter ion, so you might see potassium tert butoxide. It can also be written like this shown here. Both of these are the same thing. And so in this case, we would undergo an E2 reaction. Secondary carbons can be E1, E2, SN1, or SN2, and so we need to take a look at other things to determine which mechanism is occurring with secondary carbons. And then tertiary carbons will be SN1, E1, or E2. So before we can determine which carbon is primary, secondary, or tertiary, we need to be able to identify which carbon is attached to a leaving group. So what is a leaving group? It's something that has charge stability, and in general you want to think about the pKa of the conjugate acid of a leaving group. And so if we look at this chart down here, essentially charge stability correlates with leaving group ability, where Lg stands for leaving group. And so if we look at this, we have a triflate anion here. And so if this was our leaving group, we want to think about the conjugate acid. And so that would be triflic acid shown here. The pKa of that is about minus 15. And so that's going to be our absolute best leaving group. And if we take a look at some of the rest of these, we might look at I minus here. We know the conjugate acid of that is HI. The pKa is about minus 10. And so a very good leaving group. Think about water here. The conjugate acid of that would be H3O plus. What's the pKa of H3O plus? It would be minus 1.7. And so again, a very good leaving group. We continue up here. Obviously, this doesn't go in the exact order of pKa's because notice we have Br minus and Cl minus over here, where the conjugate acid of Cl minus would be HCl. pKa is minus 7, which is lower than negative 1.7. But in general, if your pKa of your conjugate acid of your leaving group is below 4 or so, it's going to be a decent leaving group. Notice over here we have our carboxylate anion, and so this conjugate acid of that would be a carboxylic acid, which have pKa's of about 4. And then all the way over here on the side we have F minus, and so the conjugate acid would be HF, where the pKa is about 2. And so notice the highest number we have here is our 4 for our carboxylic acid. And so in general, if you're looking for a leaving group, think about when it pops off, it takes electrons with it. And then what does that conjugate acid look like, and what is the pKa of that? If the pKa is less than 4, then it's going to be a good leaving group. In general, if you have something that is higher than F minus or more unstable than F minus, then you are not going to have a substitution or elimination reaction occur. Absolutely nothing is going to occur. So it's important that you think about leaving group ability, because if we don't have a good leaving group on our molecule, then no reaction is going to occur. I've mentioned a few times that we are able to convert bad leaving groups into good leaving groups. So let's take a look at this problem shown here. We want to look around our entire organic molecule. We identify the carbon that is partially positive. So that's the one that is here. We see that it is attached to an OH, and we know that hydroxide is a bad leaving group. And so this reaction is going to have nothing happen unless we make this into a good leaving group. If we look over top of the arrow, we see that this is negatively charged, and so we would be thinking that we're going to have an SN2 reaction, but in this case, the outcome is no reaction for this. And why is that? It's because hydroxide is a bad leaving group. And so essentially, remember that sodium means nothing, so we would mark that out. Put a minus charge on the bromine, meaning that it has an extra pair of electrons. Now we want to know who wants these extra pair of electrons. Does bromine or does oxygen? Because if we go through the mechanism, we would attack there with our Br minus, kick off our OH, and then our outcome from this would be our alkyl halide along with hydroxide. So notice we've essentially transferred this minus charge from the bromine to the oxygen. Think about the conjugate acid of Br minus, that is HBr. pKa is about -9. And so it really wants to lose that hydrogen, meaning that it's pretty happy being negatively charged. Conjugate acid of hydroxide would be water, and the pKa is 15.7. And so we know that water doesn't really want to lose this proton to go to here. So it doesn't really want this negative charge. Therefore, it's going to reside on the bromine. Nothing is going to happen here. We're going to have no reaction. Now, if we take the same molecule, this alcohol shown here, but we change the reaction conditions from sodium bromide to HBr and sulfuric acid, we will get a reaction, and we will get the product that you may think we would get. So we would get this alkyl halide shown here. So why does this occur, but it doesn't occur with sodium bromide? HBr is a very strong acid, and so our oxygen can come in and pick up a proton from the HBr. And so we grab that, we kick off the bromine, we get an intermediate that looks like this. And now if this pops off, it becomes a neutral water molecule, and water is an excellent leaving group. It's an even better leaving group than bromine. So go back and look at the chart that I just drew up a couple minutes ago. Once we're at this point, we've gone from a crappy leaving group to an excellent leaving group. So now our SN2 reaction can occur with the bromine, where it comes in, does backside attack, we kick off water, and then we get to our desired product. So keep this in mind when you're looking at reactions. We don't just kick off any type of group. It has to be a good leaving group. So I just showed you an example of a substitution reaction where we can change the reaction conditions in order to drive the reaction forward. Let's take a look at an elimination reaction here. So we look around our entire organic molecule. We find that this carbon right here is attached to this OH. So therefore it's partially positive, and this is where our reaction is going to occur. We see that this carbon is secondary, and so it might participate in SN1, SN2, E1, or E2 reactions. And we need to take a look at what is over top of the arrow. We see that we have phosphoric acid, so H3PO4. And so this is a very strong acid, and it's neutral, so it's going to promote SN1 or E1 reactions. And then we see that we have this delta symbol down here, which means heat, and so therefore would promote an E1 reaction. Also note that if you see H3PO4, so phosphoric acid, or you see sulfuric acid, so H2SO4, these things will never act as nucleophiles, and so you will always get an elimination reaction under these type of conditions. And so let's walk through the mechanism to get to the final product. So we know that hydroxide itself is a terrible leaving group, but we're in extremely acidic conditions, and so if we draw out our H3PO4, we get something that looks like this, where we have H3PO4. I've drawn this hydrogen out specifically because it's going to participate in the reaction mechanism. So if we take our alcohol, we come and grab this hydrogen here and kick off the rest of our phosphoric acid piece. And so then we get to our protonated alcohol shown here. And so we've gone from a bad leaving group to a good leaving group. And now we're ready to continue with the rest of our mechanism. Remember that we decided that this was going to be E1, and so now that we have a good leaving group, it just pops off, and that ends up giving us our carbocation intermediate. This carbocation is secondary, so we want to take a look around, see if we can make it more stable by doing a 1,2 hydride shift or a 1,2 alkyl shift. We see that if we look at so remember the carbocations on the 1 carbon, we look down to the 2 carbons, and doing a hydride shift in this case would not give us a more stable carbocation. So that's not going to happen, and so we can move on to the next step of our mechanism, which is going to be the electrophile elimination. So we grab a hydrogen from the beta carbon and move the electrons towards the carbocation. What does it? It's going to be the acid over here. So generally you want to think of these as acid catalyzed. And so once it protonates here, then once it protonates the molecule here, then it comes back and deprotonates the molecule over here. So we draw our mechanism arrows like that. We get the alkene formed. So remember that elimination reactions always result in pi bonds. So we have gone from an alcohol containing molecule to an alkene shown here. And just to label these steps, this one here is a proton transfer, so I labeled that with PT. This one here is a heterolysis step. So remember, heterolysis always occurs in the E1 mechanism. And then this here would be electrophile So that says electrophile elimination. And so we have our electrophilic molecule here, and we've done an elimination to get to our pi bond. So again, keep in mind that hydroxide itself is a bad leaving group, and by protonating it with some sort of strong acid, we can turn it into a good leaving group. So I just got done talking about alcohols. We can protonate alcohols to turn them into a good leaving group so that we have a neutral water molecule leaving. But what about amines? And so if we take a look at this amine shown here, we treat it with sodium bromide just like I did earlier with the primary alcohol. Again, in this case, we are going to get no reaction for similar reasons as earlier. Here, remember that sodium doesn't mean anything. We mark it out. We put a negative charge on this bromine. And so who wants the negative charge, the bromine or the nitrogen? If we do draw the mechanism, we would get something like this. So we would get our alkyl bromide plus our negatively charged nitrogen. Remember the pK of the conjugate acid of this would be 35. pK of the conjugate acid of this is about -9. Bromine is much happier with the minus charge than nitrogen is, so therefore we have no reaction occur. So if we switch up the conditions from sodium bromide to HBr, unlike earlier, we are not going to get the expected product. So remember when we took the alcohol, we treated it with HBr, we got the alkyl bromide. In this case, this does not happen. We do not make this molecule. Instead, what happens is our nitrogen is slightly basic, so it does come and grab the hydrogen from HBr, just as the alcohol did, and so we get a protonated amine intermediate, but this is still not a very good leaving group, and so our reaction stops at this point, and we just have this ionic salt floating around, and we never get to our alkyl halide product. So since a protonated nitrogen is still a poor leaving group, keep in mind that even under acidic conditions, amines do not participate in nucleophilic substitution or elimination reactions. And so generally when you're thinking about SN1 SN2 E1 E2, you're not going to be thinking about compounds that contain amines. Alright, so now that we know how to identify which carbon contains a good leaving group, let's talk about the different types of carbons bonded to the leaving group. So this would be primary, secondary, tertiary. What type of hybridization is it, and what is around it. So 3 factors to consider is the hybridization of the carbon. So is it sp3, sp2, or sp? number of alkyl groups attached to it, so is it primary, secondary, or tertiary, and then the proximity of double and triple bonds. So remember, if we have a benzylic carbocation or an allylic carbocation, it's going to be more stable than just a regular primary carbocation, which we'll look at in just a second. So let's first talk about the hybridization of the carbon containing the leaving group. You may have noticed that most of the time when we're drawing these type of reactions, the carbon that contains the leaving group has been sp3 hybridized. So in terms of hybridization, generally SN1 SN2 E1 and E2 reactions do not occur unless the carbon containing the leaving group is sp3 hybridized. And this is because sp2 and sp carbons have greater S character than sp3 carbons. And so they can form stronger sigma bonds with the leaving group, which therefore makes it harder for the leaving group to depart. And then E2 is the only true exception to this rule. And so remember that we saw where we could take alkenes with a leaving group. So this would be an sp2 hybridized carbon. We can then take some sort of base, do an E2 reaction to kick off the leaving group. And so we go from an alkene to an alkyne molecule. And so this is an example where an sp2 hybridized carbon participates in these type of reactions. But generally for SN1, SN2, and E1, you're only going to see sp3 carbons participate. So let's talk about the number of alkyl groups that are attached. And so for an SN2 reaction, the big limiting factor here is steric hindrance. And so in general, tertiary carbons that contain the leaving group will not undergo SN2 reactions. And so therefore SN2 reactions are only possible with primary and secondary carbons containing the leaving group. So for example, I have made this molecule here. We'll just call this blue ball a bromine, so this would be ethyl bromide. We see that this carbon is primary right here, and so we're thinking it would undergo an SN2 reaction. If my tennis ball right here is my nucleophile, keep in mind that things like iodide and bromide are really large, and so they might actually be this big compared to our carbon and hydrogen atoms. If it comes in backside attack, so remember 180 degrees behind our leaving group, if the blue ball is our leaving group, our tennis ball must come in 180 degrees behind, and then it is able to attack this carbon right here because there's not very much steric hindrance. If instead we look at a tertiary carbon, so we see this one here, it's attached to our bromine. The central carbon is then attached to 3 other carbon groups, and so therefore it is tertiary. If we take our same tennis ball nucleophile and it tries to come in and attack from the back, I'm bumping into these hydrogen atoms right here, and so I'm not ever able to get in and attack that carbon atom. So keep in mind that tertiary carbons are very sterically hindered, and therefore we're not able to get backside attack. So with E1 and SN1 reactions, we know that from the rate laws, both of these reactions are dependent on the exact same thing, and that is the ability of the leaving group to just pop off and leave a carbocation behind. And so the big limiting thing for these type of reactions is carbocation stability. Remember that tertiary carbocations are most stable, and so they will undergo E1 and SN1 reactions the fastest. Remember that primary carbocations are extremely unstable, and so therefore primary carbons will never participate in an SN1 or E1 reaction. Alright, so SN2 reactions cannot occur with tertiary carbons containing the leaving group. SN1 and E1 reactions cannot work with primary carbons containing the leaving group, but E2 reactions can work with primary, secondary, or tertiary carbons that are containing the leaving group. And this is because in an E2 reaction, we're simply just pulling off a proton from the beta carbon, and protons are small and well exposed, and so we're able to access them no matter how much bulk is around the carbon containing the leaving group. So again, if we take our ethyl bromide molecule here that I showed earlier, we see that the leaving group right here is attached to this carbon, which we call the alpha carbon. We then go over to the beta carbon and we pull a hydrogen off of there. If we use our tennis ball as our base in this case, it's going to want to come in and grab a proton right here. Notice that it has no difficulty being able to get to this point, and so an E2 reaction can occur with a primary carbon. And then if we go back to our tertiary carbon here, so it's containing our leaving group, has 3 different carbons attached to it, these can still participate in E2 reactions. So our leaving group right here is attached to our alpha carbon. We then need to go to a beta carbon. We have 3 different options in this case. They're all identical, so I'll just go to the one up here at the top. And again, our tennis ball base comes in and wants to grab a proton. Notice that it has no difficulty being able to get here because these protons are small and well exposed, and so therefore E2 reactions can occur with primary, secondary, or tertiary carbons that contain the leaving group. All right, lastly, let's talk about the proximity to double bonds and triple bonds. So if our leaving group here is attached to a carbon that's next to an alkene, we call this allylic. And so these are not normal primary carbons, these are actually allylic. And then here, if our leaving group is attached to this carbon, we call this benzylic. And so if we have a leaving group attached to an allylic carbon, which is this one right here, or a benzylic carbon, which is this one right here, then we have added stability. And so in this case, if our leaving group just pops off, we get a carbocation that looks like this. We call this an allyl cation. And this is not a normal primary carbocation because there is a resonance structure. We can swing this double bond over here. And so now we would have something that looks like this. And so in the case of an allylic leaving group, it can participate in SN1 reactions because of this added stability. And it does not act like a normal primary carbon. Same thing in the benzylic position. If our leaving group just pops off, we get a cation that looks like this right here. And then we can draw several resonance structures where we push it down into the ring, therefore making it more stable. And again, these type of substrates can participate in SN1 reactions. So keep that in mind that even though these look like primary carbons, they are special, they're allylic and benzylic, and therefore can participate in SN1 reactions.